As we discussed in our last lecture, the shape of a formation can be modeled by inter-agent distance between every pair of agents. This specification can be naturally modeled by a weighted graph. So we use a weighted graph to model the shapes of formation. So we have the V is a set of agents. And E is the edge set. And D is the distance between every pair of agents. If we give the interdistance between every pair of agents, then the graph is a complete graph. So you may be wondering, is it necessary to specify the distance for every pairs of graphs? Actually, it's not. There are two reasons you can think of. The first reason is in a very large network, there are many agents. So it's unnecessary to specify the distance between every agent to maintain a proper shape. Another reason is that the agents, they may have a large distance. If you want to specify the distance between them, it means two of them need to communicate. So in this case, the sensing or you need high power communication capacities for these two agents. It will be cost effective to remove those edges if this is not at all possible. So therefore, we can use a graph, not complete graph, only specify some of the edges. Then we will introduce the concept of graph rigidity. Graph rigidity. So now let's specify the formation by graphs. We have the set of agents and the number of edges we want to specify the interdistance between them. So D is a matrix, is a weighted matrix. We can consider D as a mapping from the edge set to from every edge to a possible number to specify a feasible desired inter-agent distance to each edge. Then this is the formation. For a specific formation, so we can, they maybe have many realization. What do we call realization? So realization is just a feasible point, a set of feasible point. For example, P1 until Pn in dimension 2 or 3. If M is 2, it's planar case. If 3, it's in 3-dimensional. So we assign each one agent to a particular point so that the in the distance constraint is satisfied. The distance between agent Vi and Vj is Dij. So Dij will be some elements in the matrix big D. This is the weighted matrix. So you can think for a particular formation, there may be many realizations. Then we call a graph G and the realization P as a framework. This is a definition of framework. Then we can define configuration space. is the set of all possible realization of a framework with rigid motion. Rigid motion means this shape, they can only have translational motion and rotational motion. Here we factor out by pin down an arbitrary edge. For example, let's in this case, we have triangular shape. So let's fix this edge. So this edge is fixed. Then in this case, if we fix this edge, so we can find one realization. Okay, suppose this is 0, 0. So this is 1, 0. So this is half square root of 3 and half. So this is one graph. So graph we can define as V, we have 3 agent, V1, V2, V3. Then for the edge set, we can define V1, V2. Let's say this is the 1, 2, 3, V1, V2, V1, V3, and V2, V3. Yeah. Then the distance between V1 and V2, D12 is 1, and V13 is 1, and V23 is 1. And then the P, we have 0, 0, half square root 2, and 1, 0 in planar space. That will be one realization. So in this case, if we pin down one edge, the graph has no rotational motion and translational motion. So in configuration P and P. Now let me give you another example. Still in this case, we have agent 1, 2, 3. For example, I have agent 1, agent 2, and agent 3. So in this case, the V is still V1, V2, and V3. So the edge set here, we only use V1, 2, and V1, V2, 3. Okay. So let's specify the D matrix. It's D1, 2 is 1, and D2, 3 is 1. Let's pick this as 0, 0, this 1, 0, 2, 0. Okay, then we have the realization P will be one realization 0, 0. Then we have 1, 0. We have 2, 0. Okay, so this is the framework. From the G, we define the graph here, and the P, it's called a framework. Now, in this case, what will be the configuration space? Okay, let's pin down this edge. Let's fix this edge. Let's fix this edge. Okay. Then we know the distance between 1 and 2 is 1. Now then we can rotate. Okay. We can rotate the node 3 with agent 2 at the center. The radius is 1. So agent 3 can be anywhere on this circle. Okay. So in this case, the configuration space will be this graph we defined, and with all possible realization. Okay. There'll be, say, so the realization is just which the graph is fixed. Now we change the P. So P could be anything 0, 0, first one, because we pin down the second one. So the last one can be anything. Yeah, I think it can be written as, let's say, here we have 1 plus cosine theta, 1 plus and 0 sin theta. Yeah, we'll switch from 0 to 2 pi. So theta 0 it will be 2, 0. Then at this point, we have, if theta is sine, if theta is, let's say, theta is 2 pi, then we have 1 and 1. Yeah. Then theta is pi. We have 0 and 0. Yeah, and so on. So this forms the configuration space. So if the rigid framework, so the framework we know, we call the framework it's rigid if the graph and the realization in the configuration space is a single isolated point. That's the example I gave to you. This one, if we pin down this edge, it's just a single point. So this is a rigid framework. The other example I gave to you, this is flexible. Yeah, if we pin down this, so the configuration space is not a single isolated point. So this is the flexible framework. So this is the rigid framework. Yeah. So as we see from those examples, the rigidity is defined for the framework. So framework contains the graph and configuration, not by the graph alone. Now let's see these cases in R2 in planar cases. So for the first one, it is for this, for the graph. Okay, let's see how agent 1, 2, 3, 4, 5. So the graph we have G, the vertical side, V, E, and D. Yeah. So we can have V1, and V5. For edge, we have V12 and V15 and V14 and V23, V24. Then we have V34, V35. Then we can specify the distance between these edges. We will see for these two framework. Let's assume we have agent 1 and 3 at the same location. This is agent 2, agent 4, and agent 5. And if we put 1 and 3 at the same location, but there's no edge, okay? Does not belong to the edge set, okay? We just put them together, but there's no edge between them, okay? We have the same graph. We can see we have exactly the same graph G, but the realization is different. So in this case, if we put agent 1 as origin, yeah, you can see they have exactly the same graph, but different realization. So in this case, this one is a rigid framework, but this one is flexible framework. Because we can rotate agent 5, pick agent 1 and agent 3 as a center by rotating agent 5 with a radius, the distance between agent 1 and agent 5 and agent 3 and agent 5, because they have same distance. Then we have many realizations. So 5 could be here. It will not change the inner distance we specified by the matrix, the weighted matrix D in the graph, V, E, and D. So in this case, this graph is a rigid graph. No, not graph, it's framework, okay? The framework contains a graph and configuration. If we use this configuration, it's a flexible framework. Now let's see this graph again. It had the same, not same graph, okay? Now we change the matrix D. If we change the matrix D, they're only rigid realization. So therefore, for this framework, it's a rigid framework. If we pin down any of the edge, so the agent cannot move. You cannot rotate it. You cannot. There's no translational movement for any of the nodes. There's no rotational motion for any of the mode. So the only possible realization to make this one, the graph and the configuration, is rigid framework. Now let's do some exercise. So let's consider first case in R2 in the planar case. So it's very easy to see if we pin down this edge. So this agent may move as a circle using this agent as a center, and here using the distance between this agent and this agent as a radius. So therefore, in the configuration space, the framework is not isolated point. So therefore, this is flexible framework. This is flexible framework. Now let's look at this case. Yeah. In this case, a flexible framework of a rigid framework. It depends. Now let's consider this case in R2. If in R2, if we fix this edge, so there's no rotational motion or translational motion. If every agent moves, it will now satisfy this constraint specified by D. Therefore, in R2, it's a rigid framework. Please remember, framework is defined by the graph and the realization. Now let's consider the case in 3D. So in 3D, if we pin down this edge, so this framework is a flexible framework. Keep the distance so we can lift this agent out of paper. Okay, you can think in 3D dimension, we can lift this agent by keeping the distance. So using this link as an axis, so we can rotate around this axis. So by keeping the distance from this agent and these two agents. So therefore, it's flexible framework in R3, but it's rigid framework in R2.